Welcome back to Stage Bob at our Quantum Summit. We continue here with 3 more interesting talks, and I would like to encourage you once again to engage in discussions and questions already in the live discussion, in the live chat, so that if there is time at the end of the talk, we can already address the questions maybe. Otherwise, of course, there's always time afterwards to go to the speaker's corner and ask your questions there, but it's still nice to already have a discussion going here. So I am happy to welcome our first speaker of this last block, so to say, of the Stage Bob here. And his name is Christian Tuchku. He's a theoretical solid-state physicist, and he completed his PhD just this year, I see. So congratulations, Christian. He's a quantum software engineer at the Fraunhofer Institute for Industrial Engineering, IAO in Stuttgart. And he's engineering use case-based quantum algorithms. The talk he's gonna give us and he's gonna hold is called Schrödinger's Cat in Industry, Real-Life Quantum Software Engineering. So that already sounds very enticing and interesting. I'm looking forward to it. Welcome, Christian, and the stage is yours.
Yeah, thanks a lot for this great introduction. Thanks for giving me the opportunity. It's a pleasure to present to you how Schrödinger's cat can be applied, or at least is life and death at the same time in industry. Yeah. So the outline of this talk goes like we will take a short introduction to the physics of quantum computers. I mean, you're mostly aware of this, I guess, since we are in the very end of the session already. But then we will focus a bit on the IBM quantum system in Eningen, where we as a Fraunhofer have administration for this. Then after that, I will briefly present you our, or not briefly, but show you our, what are we doing at the Fraunhofer IAO in Stuttgart, and what are we doing in the scope of the SEQUOIA research project and the Kompetenzzentrum, which is at the same time presented, I think, so the Kompetenzzentrum itself as a project on Stage Alice. So who's interested in quantum computing will be one of the questions this talk should clarify, as well as what are criteria for potential use cases nowadays. When is a use case which can be at least tackled by current quantum computers or near-term quantum computers? What are timescales which we are, where can we expect quantum computers really where do they enter the industry, at least in the next few years? And then in the end, we will come to recommendations for companies. What can we do now to be at least prepared for the quantum revolution, which is expected to appear tomorrow? So let's start with a short introduction to the physics of quantum computers. As the talk already states, we start with Schrödinger's cat. Schrödinger's cat is dead and alive at the same time, meaning if we do not look at the box where the cat is placed in, we don't know if it is dead after a certain time when a radioactive substance decayed, right? So, and this is all you need to know, at least from the theoretical solid-state physics, if you want to understand quantum computation, because it's in both states at the same time. That means usually, or if you have a combinatorial problem, then you can think about, if you want to solve it, you need to go each of these branches of this decision tree at a time. But if you have a system which is in so-called superposition, where all the possible inputs can be realized at the same time, you can process the whole tree at once and operate in all states simultaneously. So this is what's quantum computing about. But this does not help much because if you open the box, if you measure your system, you measure only one state as in a classical computer. So you need to be very clever as a quantum software engineer to find the right, what we call interference pattern, to find an operation which distills you in the end the state which you're aiming for. So that's how we need to build circuits and quantum algorithms. And you can use not only superposition, but also entanglement, meaning if you have a certain state which consists of 2 qubits here, they are more or less like, you can entangle them via, so for example, C0 gates. That means that if you measure position 1, you also measure position qubit 2, due to the fact that you cannot measure one without changing the other one, what's called entanglement, and therefore you can study highly dependent systems. So the current players on the market, at least from the hardware side, are listed here. So not all, but the most important players, say in the superconducting architectures, we are mostly aware of them. Things which need to be which are very cold, which will be accessed to a cloud base because they need helium. For example, IBM already get here two representatives. But trapped ions are also very important nowadays, as they predict a quantum volume of already 4 million. And maybe these ones, they do not rely so much on the cooling. And not only quantum computations that are gate-based are important, also quantum annealing has currently much more qubits. It's not universal, but in a sense, it's also very powerful. It can be used currently already in industry, as we will see in a moment. And so to come to the system, which is annealing the system, IBM Q system, it's just started, was available this year in January. We are, as a Fraunhofer, there an administrator. You can get also tickets if you want to work without Q, say, and for a commercial access here. You can get tickets over the Fraunhofer. And so this one has an amount of 27 qubits. That is a number we will need later in the end. But this is not much, at least, but this is the state of the art of IBM. So it has this competitive quantum volume of 32, which is, say, the state of the art of the IBM hardware these days. And if you look at the decoherence time, so that's the time how long a qubit can save the information, more or less, and the gate time, how long you need to operate at a certain quantum operation, you see that, say, that the amount of operations you can do before you lose the information perfectly would be around 200. So that's not that deep. So you need to improve these decoherence times. That's why we're in the disk era. But it's not only about the decoherence. Also, the gates have errors. So they are, say, in the close to percentage, but in a sub-percentage area. But still, you're restricted nowadays to the NIST, noisy intermediate scale quantum computing era. That means you need to make short quantum circuits and embed them usually in classical systems. That's what we call hybrid quantum computation. And also, if you want to program algorithms, you need to be aware of the coupling map. So you cannot simply couple every qubit with every qubit due to the hardware. So we are programming very close to the hardware to also take into account the actual structure, more or less. And for example, you see here a short experience from the Eniga backend. So we try to solve the Sudoku problem, which has this 2x2. These are the expected solutions. For this, you write a code in a Python language, more or less, produce your quantum circuits, and then you measure. And in the end, you see that you get all the right results with a high probability, but due to the errors, due to the background, you get also a lot of noise here. It's not that much, but if you want to scale the system, this will be a tough task to solve in future. And so we are working as the Fraunhofer IAO here. We are working in the scope of competence center quantum computing Baden-Württemberg, as I said, which is introduced on stage Alice. And there are several funded research projects. We are one of them with total funding of 6 million. The overall funding is about 90 million. And we are funded by the Ministry of Baden-Württemberg. And this is a foundation for 2 years. And we are mostly looking at engineering of industrial and hybrid. It's important to emphasize industrial and hybrid quantum applications, because what we're doing is we are developing methods, tools, and processes with a very special aim to apply them already in industry. So we are developing, we are going to applications, we are linking ourselves to interested industry companies, and we are also educating in the industry and with our consortium partners, either the conventional programmers on the high level or also quantum software developers for more low-level quantum algorithms. We are developing software's lifecycles, creating tools which, like, use the Qiskit Aqua bibliography. We are enlarging this bibliography, specialized to certain use cases, and we are developing software for this in kind of software lifecycles. We are also funded for 2 years and are working strongly together with the University of Tübingen, with the Stuttgart IIS, with the HLRS, with the Fraunhofer FCD, IF, IPA, and we as an IAO. And in one of our kickoffs, so that was very interesting for us. It's not representative, but that was a survey in the kickoff of our SEQUOIA research project. We asked, okay, where do you come from these companies, and why are you interested in quantum computing? And there, it distilled. So we saw that most of the companies which are aiming for applying quantum computing are large ones, but also a significant amount of small or medium-sized IT companies which are trying to provide quantum algorithms later on. Obviously, you also have these research institutions, politics, and press, which is for sure here not very representative, but that's the take-home message at least. And these large companies are interested in use cases we are developing them together with the industry. And you can separate these use cases in different sectors, energy, for example, in the energy sector. So roughly speaking, how to distribute or control, say, a certain distribution of e-mobile charging stations, of vaccination stations, of hydrogen pipelines, of wind farms, how to also not only locally, but also how to control, say, the energy, how to control these systems. And it's not only energy, it's also logistics. Say, if you want to have an optimal route planning for an industry, you also, if you want to simulate things like smart cities or the traffic flow in these cities, you have also very large systems, which a lot of input, big data, which you need to operate on at the same time. So this is also something which is a potential use case. It's also in the area of production, which is very important in the state of Baden-Württemberg. There you have either the thing which, quantum computing was initially invented for, so Feynman predicted, for the material, for the molecule simulations, but also, say, for example, for the topology optimization of workpieces, if you want to reduce, say, for example, the surface of a certain workpiece in comparison to its volume. Or also the optimization of scattering routines, the famous paint shop problems, which was one of the talks in the session, I guess, by WB. And there's all very famous use cases, or also in the area of finance, if you want to evaluate a portfolio or risk models, which is also an expected problem for quantum computing. And there's also a very important problem in cryptography. This is not only an option of better performance, speed up, it's a threat. You're already, not yet, theoretically, you're already on the stage that you can decrypt RSA encoded informations. It's not, the hardware is not ready yet, but it will be soon, and therefore you should be prepared already. It should make your data safe now, such that they cannot be saved and then decrypted later. And you can use this kind of entanglement, for example, also for information teleportation called. So if you read out one part of the qubit, the other one is read out as well. And all these use cases rely on a certain pool of algorithms, which were already invented in the years ago. So that's a Grover for unstructured search. That's a short for factorization. And you have variational algorithms like quantum Eigensolvers or quantum Fourier transformations. We don't to go into very detail to this, but we are actually working on how can these algorithms applied, and we are also trying to, based on these algorithms, try to develop new algorithms. And the question is, okay, you had these use cases. What is a criterion for a use case to be successfully implemented on a quantum computer? And as I said, for example, one of the main criteria is you need a high-dimensional configuration space. That means a lot of data which need to be manipulated at the same time with a parallelization, and they can be very connected. The entanglement helps you also to calculate very highly dependent algorithms. On the other hand, you can have exponential or polynomial speedups in certain regimes like decryption and so on, Grover, Shor. And therefore, you can have a real-time resolutions of certain things like traffic simulations or logistics, route planning, which is real-time resolved, like satellite things as well. And security, as I mentioned, is a threat and not an option. You should be prepared for this kind of for this area of post-quantum cryptography. And if you're only interested in, say, approximate solutions, algorithms which rely on approximate solutions are also very natural to solve, or better to solve on a quantum computer due to the pre-existing algorithms and the nature of quantum physics, like it's what Heisenberg called Unschärferelation. So German physicists, and so this kind of things which are rely on disk machines. What is no indicator for being better solved on a quantum computer is the class of NP complex problems. This might be the case. So things which are in the complex class of BQP might be, NP might be in BQP, but there's not proven yet. And and the other natural questions to ask for is what are the timescales for this? And here you see it. So the so-called quantum technology readiness level predicted by the superconductor set in Jülich. And there you see that the different hardwares are on a different level of near-term or industry realization. So while these annealers are already in use or very high level to be already applied to the industry. So the IBM Rigetti and so the superconducting qubits here, for example, they still need a bit of time, but they predict certain roadmaps with an exponential growth, and therefore they are expected to be, say, in the next 5 to 10 years, very competitive. But so let me emphasize that for a 42 qubit system, you already need such a supercomputer like Jubin, which have 300,000 CPUs and can operate like 10 to the power 15 operations per second, which is an incredibly large number. And you need this kind of CPUs to simulate 42 qubits. Inningham has 27, and IBM and Google, so nowadays, and IBM and Qubit are, by the end of 2030, are predicting, and they are faster than they predict so far, they are predicting 1 million qubits, which is extremely large and no way to simulate this classically anymore. And therefore, it will be a fundamental quantum revolution. But this will still take 5 to 10 years. But already, so they have all, let's say, a quantum volume of 10 to the power 2, so 100, say, roughly speaking. So 60 to 70 or 120. But it needs to be a potential of 2. But INQ already predicted, so that's in trapped ions, a quantum volume of 4 million, whatever this is, but it's amazingly large. So you would see that this will come soon. And so the recommendations which we want to give you as a company here are you can decide on which level you want to follow quantum computing, on which level you want to educate yourself. And so what can you do to be prepared today, to be prepared for tomorrow? Decide what do you want to have. So do you want to stay informed, meaning do you want to understand the physics, so the principles, and keep an eye on the development, say wait and see what's happening? Then you might join only high-level webinars. For example, we at the IO, this is not everything, but just an illustrative thing. For example, we are giving talks, so-called talks, like quantum cryptography or how to learn in industry to deal with quantum computations. Or you follow public channels. We are also blogging, for example, but we are not the only source for this, only as an example. Then you can say, okay, I want to have more, I want to have assessment, I want to understand the state of the art of quantum computers, and really I want to estimate, qualified, if it's interesting for me, if there's a relevant thing for me. And there, for example, what I could really recommend are this kind of specialized QC talks, which have a low level, which go to the low level physics. If you want to stay qualified, you need to learn what the algorithms are. You need you can identify if they are relevant for you in your classical codes. Therefore, you should join either schools at the IO, but also IBM provides these kind of summer schools, for example. And if you really want to perform, that's where I want to end with. Then you should if you want to embed your quantum solutions in classical things, if you want to write your own quantum programs, you need simulators to test, for example, and in the end with backends to calculate, which, for example, Inningen, but we are also providing tickets if you wish. And with this, I want to end. So this is our team on the IAO, so the quantum computation team. And we're really looking forward to interesting discussions, collaborations, and thanks for your attention.
Thank you very much, Christian. That was very, very nice to hear, to see also the many potential use cases that you've showed here. And I think it's a very important job that you're doing, especially for a country like Germany, that you focus on the software engineering and development here. As we know, Germany is traditionally very strong in like hardware development, not that strong in software development. So I think you can really make a difference here for the future in at least for the quantum technologies. Thank you very much for the talk. We have one question here. I don't know. I think we can have a quick question. It says, which steps would you suggest to prepare for the post-quantum decryption thread?
Yeah. So first of all, one should yes. So one should be prepared today. As I said, so if somebody stores your information and some informations are not that important, but if informations are stored today and can be decryptified in 5 to 10 years, that's bad. So you should try to now use new schemes or different than RSA to decrypt your informations. And there are different approaches. But this goes too long, I guess, to go into very detail. But RSA for sure should be exchanged. So,
Well, thank you for this short answer. Of course, you can go more into detail in the Speaker's Corner, which you will head on to now, and also tomorrow on the same stage here on Stage Bob, we will have more on quantum communication and also post-quantum cryptography. So if you're interested, please feel free to join us here tomorrow too. So thanks again, Christian.